We're going to look at the essential mathematical concepts necessary to understand machine learning algorithms. And the first concept is that of a variable. A variable is an object, a mathematical object, that represents a value, and it can have a very specific value assigned to it. We can also have lists of variables. In this case, we are referring to each element in the list using the subscript index. So x2 will be the second element on that list. We have also the summation operator, which will help us denote adding together multiple values within a list. So in this case, we can add together all the values within the list X with the summation and denoting the subscript from I sub 1 to n, as you can see in the slide. Then we have vectors, which in a sense are like lists. The only difference will be that in a vector, the order in which the elements appear in the list is very important. And each position within the vector has a specific meaning to it. In terms of the notation, is very similar. And on the right-hand side of that slide, you can see how we can graphically represent a vector, in this case a three-dimensional vector, and each position within that vector, each value within that vector represents a different dimension within the representation space. Now, to multiply vectors, we need to use what we call the dot or the scalar product. So in this case, in the slide, you can see that we have two vectors, x and y. They both have n elements or n values, so we say that the vectors have length n. And so the dot product between x and y are the summation of all the individual products of each element within both vectors. So that's x1 times y1 plus x2 times y2, etc. And of course, we can denote this using the summation operator, as you can see in the slide. An important thing to note here is that we have, when we do the dot product of these two vectors of length n, the result is a single value, so a scalar value. Then we have matrices. You can think of matrices as tables. So in the same way you have rows and columns in tables, you have rows and columns in matrices. Matrices are usually denoted with capital letters in bold. So in this case we have X, and matrices have dimensions or shape. So in this case, the matrix in the slide has n rows and m columns. So we will say has shape n times m. If you look at the right-hand side of the slide, the first row will tell you how you can denote a single element of the matrix. The second row, the second line will tell you how you can select an individual row. So that introduces the concept of star as a wildcard. So in this case, X I star means row I and all the possible columns. So the result is a single row from the matrix, and we call this a row vector. We can also use that to denote a single column, as you can see in the next line, and we will call that a column vector. And finally, the concept of the transpose of a matrix is exactly the same as the transpose in a table, which is just flipping around rows and columns. Now, multiplying matrices is a bit more complex than multiplying vectors, or it can be a little bit more complex. So there are two types of products for matrices. the Hadamard product, now imagine that we have two matrices, A and B, and they both have n rows and m columns. So we denote the Hadamard product with that funny symbol there, which is kind of like a circle with a dot in the middle. So if we multiply A times B using the Hadamard product, what we get is another matrix C, where the first element or the element in the first row and first column is simply the product of the element, the first row and first column from matrix A times the first row, first column of matrix B. So the first element in matrix C is the first element of matrix A multiplied by the first element in matrix B. So note that all the dimensions across all the three columns in this slide, A, B, and C, they all have the same dimensions. And of course, this is characteristic of the Hadamard product. So you can only multiply two matrices using the Hadamard product if they have identical dimensions. And the result of that multiplication will have, again, the same dimensions. So it will also be a matrix with the same dimensions. So this is kind of like a piecewise multiplication or an element-wise multiplication of the two matrices. And you have a visual representation on the bottom of the slide. Note that same as with numbers, basically, if we use the Hadamard product, A times B will give you the same result as B times A. But then we have the dot product, which is more commonly used for matrix operations. And in this case, now we have two matrices, A and B. The dimensions are slightly different. Dimensions of matrix A is n times m, whereas the dimensions of matrix B is m times k. So now, what happens when we multiply A times B is that the first element is the product, the dot product or the scalar product of the first row vector of matrix A and the first column vector of matrix B, as you can see. So I would like you to pay attention to the subscripts here now. So as we move in the resulting matrix, as we moved in the second dimension, so across columns, you will notice that the subscript of A is not changing. It's always making reference to the first row of A. Whereas when we move across rows, then the subscript of A is changing according to the row that we're referring to in the resulting matrix C. And the opposite is true for B. As we move across the columns, the subscript is changing. So we are referring to different columns of matrix B. And as we move across rows, the superscript is not changing. So we can also see that here, where each element, or the element yj of the resulting matrix C is composed of the scalar product of the row vector I from matrix A and the column vector j from matrix B. And of course, that means that the dimensions now are a little bit different. So as we saw, that when we multiply two matrices using the dot product, the second dimension of the left-hand side matrix should be equal to the first dimension of the right-hand side matrix. So that M equals M in the slide that I'm highlighting there. And then the resulting matrix, C, will have the first dimension of the first matrix and the second dimension of the second matrix. So in this case, it will be N times K. That means that even though we can multiply A times B, that doesn't necessarily mean that we can also multiply B times A. And in this case, indeed, we will only be able to multiply B times A if K and N are equal. Let's talk about functions now. A function represents a mathematical operation or a transformation. In the slide, you can see an example of f of x where the resulting value of the function depends on the value of x. So if we assign, for example, the value 2, the output of f of x will be 23. And we can, if we try all the different values, we can then represent the results graphically, as you can see on the right-hand side of the slide. We can also have multivariable functions. So in this case, we have f of x and y. And we can also represent this graphically if we count all the possible values for x and y and with all the possible combinations. We can also have function parameters. And the difference will be that these parameters will be intended to be fixed beforehand. So in this case, we have f of x and y given parameters a, b, and c, and therefore we can, in a sense, we can change any values that we want of, we can try any values that we want of a, b, and c, but the idea is that a, b, and c are not variables that will change normally, not like x and y. So on the right-hand side, we can see an example of this function with a equals 2, b equals to 3, and c equals to 5. Then we can talk about the concept of minimizing and maximizing. So we can minimize a function, and that will give us the minimum value that that function can achieve. We can also minimize a function that has parameters, and we can say, well, minimize that function, and I will and feel free to change the values of those parameters that will give you the minimum, that will provide the minimum value for the function. Okay, so it's giving you the freedom to change the values of the parameters as you try to minimize the function. And we can indeed ask for the values of those parameters for that minimize the function. So in this case, we talk about the arguments that minimize the function f of x and y. And of course, we can say exactly the same about maximizing. We have the concept of the function derivative. So we're not going to talk about how to calculate derivatives of functions, but what these derivatives represent is important. So if we have a function f of x, the derivative of that function f represents the slope of the line that is tangential to the curve. So if you see on the right-hand side, we have the representation of that function. And we have 5 points highlighted in that curve. And for each point, we have a straight line that touches each of the points. So those lines are tangential to the curve in that at those points. So if we look at if we set the value of x for each of, if we take the value of x for each of those points and we enter that value into the derivative, the value that we get out will be the slope of each of those curves. So yeah, it will be the slope of each of those curves. So if we try, for example, what is the slope when x equals 0, we'll see that the value of the derivative will be 0. And indeed, there is no slope. The value of the line that is tangential to the curve when x equals 0 is completely flat, and therefore there is no slope. And for positive values, the slope will be positive, showing that it's going up as x increases. And for negative values, the slope is negative, showing that the curve is going down as x increases. And then, of course, we can have, when the derivative, when we have multiple variables. So in this case, we have f of x and y, and we can calculate the derivative of f with respect to one of those two variables. So in the example on the slide will be with respect to x. And that will give us, again, the slope of the of f of x and y for a particular value of x. And another important concept here is that of the chain rule when we're doing derivatives. So if you focus now on the right-hand side, we see that we have a number of equations. So we have y as f of x, we have z as h of y and another variable a, and we have k that depends on z. So if we are able to calculate the derivative of k with respect to x. So now that we're going all the way from k, which was the last one, to x, which was the first variable used at the top. And this will be the same as the derivative of k with respect to z, which is what we have, what we can see directly is the dependency that we can directly see in the equation as it is written, times the derivative of z with respect to y, which again, it's a direct dependency that we can see in the definition of z on the second line, times the derivative of y with respect of x, which is again what we can see at the top. So you can see how the derivatives connect to form the derivative of k with respect to x. So this is what is known as the chain rule in derivatives. And we can, of course, put all of these together. So if we have, we can have a matrix X that has n rows and m columns. We can have a column vector y with length n. We can have a row vector w with length m. And then we can define y hat as a function of x given some parameters w. And we can say that actually the definition of this is the dot product between x and w transposed, and think about why the transpose is necessary, and it's because of the dimensions of x and w. Remember that the second dimension of the left-hand side should be the same as the first dimension of the right-hand side, so we need to transpose w. And note that this operation will give us now a column vector of length n. And then we can also define the function e of y and y hat, as you can see. And here we're using summations. And again, this will give us now a scalar value, right? And note that we are referring to individual elements through the summation and through the subscript I, we are referring to different elements in y and y hat. So yeah, as I said, y hat, it's an n times 1 column vector, and e is a scalar value. It's interesting to keep track of what is it that you get on each of these operations, as we will see later on. And then we can expand this as we wish. So if we have e of y and y hat, we can expand y hat with its definition based on h as a function. We can even introduce h inside, and we can say now that that e is a function of y and x, given another function h and some parameters w. We can then use this expansion on the definition of e and expand y hat with the actual value based on the superscript I. And then, of course, we can expand this. We can keep doing this until we get to a notation that we may find more interesting, like potentially the one we have at the end, where at the bottom there on the right-hand side, where we have effectively replaced the summation with all matrix operations. We can, of course, find, apply minimum and maximums and find potentially the arguments of the parameters or the values of the parameters w that minimize the function e of y and y hat. The output of this will be a 1 times m row vector, so a row vector of length m. Why? Because the output of this will be values, or it will be a row vector w, which, as we can see on the left-hand side, is a row vector of length m. And of course, we can also do the derivative of e with respect to w. So now it's time for you to see whether you have followed whether you have internalized all this notation, and think whether the following equation is correct. And the answer is yes. These two equations, it's correct because the left-hand side and the right-hand side are equivalent when we use the dot product between the two, or the scalar product between the two vectors, x and w. What about this equation now? The answer, I guess, again, is yes. This equation is correct. The left-hand side and the right-hand side is equivalent, and the trick here is that x prime is introducing another value with a constant of 1, and w prime has an extra value because I now starts at 0 instead of 1 when comparing w and w prime. So this is a trick that we will use. It's used in machine learning, particularly in artificial neural networks, and it's a way of incorporating that constant term, that bias term b on the left-hand side, into a more concise notation that is composed solely on matrix multiplications, without leaving any other coefficient or any other argument outside of it. So what about this now? Is this correct? The answer is no. This is not correct. The reason why this is not correct is because if you look at the right-hand side, at the numerator, you cannot do that you cannot do that dot product between those two matrices. So x minus y, that's that's a column vector of length n. So you can see there's a matrix of n rows on one column. So you cannot multiply that with its own transpose. Sorry, you can multiply it, but the value that you get is not a scalar value. So when you have when you multiply an n times 1 matrix, or a column vector, with a 1 times n matrix, or a row vector, the result is going to be an n times n matrix, and therefore it's not a scalar value and it's not equivalent to what we can see on the left hand side of that equation. What we should have written here is multiplying the transpose of the difference with the difference itself. And now we do have a scalar value, and now the equation is correct.